Hello and welcome to Emerson's section of the project, which is providing visualizations of CT imaging data and displaying them on our webpage. The components of the application that I'll be going through are the preprocessor and the web viewer. The data sets that we were provided were a 4D orthopedic data set for understanding the complex motion of the wrist, and a 3D kidney stones data set, which meshes had already been produced for by Innersight's lab. The function of the preprocessor is to take the raw imaging data as input and produce the most useful representations of that data as output. A few of the condensed requirements on the input, extracting important information accurately from the data provided, and the data conforms to the DICOM International Imaging Standard. And for the output, volume rendered models and image files in all three slice planes. The files must be compressed enough for fast display on the HoloLens and in a file format that is supported by the Unity engine. A few of the constraints, contextual constraints relating to the medical setting. Firstly, accuracy, secondly, time and security, and then the technical constraints, the HoloLens processing power, cloud storage retrieval, and medical standards for imaging, for example, ethics. A few of the technologies that were used in the implementation. So the main language here is Python. For the data analysis, interfacing it with a web application is Node.js, which is a natural pairing. And then the libraries that we used: Scikit-Image, VTK, Simple ITK, PyDICOM, and OpenCV on the image processing side, and then on more generic libraries, NumPy, Matplotlib, and SciPy. A modular approach was taken in order to implement the preprocessor, first to validate the input and fail fast on incorrect file types or modalities, and then to organize the data into a set of 3D voxel arrays pertaining to a 4D dataset so that it's manipulable. Transforming the data so that it is most useful, including morphological operations and segmentation techniques. And then outputting the data so that it can be created, so that HoloLens can create usable holograms. In order to build the first two modules, it was necessary to decode the images from DICOM standard format, conserving the metadata required to organize the slices effectively. This is shown here on the right. The images are read in and inspected based on the modality, patient ID, time, and the Z position of each slice. Several algorithms were exploited in order to create the most useful visualizations in the manipulation module. Threshold mask algorithm. This first plots a histogram of the voxel intensities, identifies peaks of regions of interest, and then masks these peaks, creating separate segments from each one. The masks then undergo morphological operations in order to smooth the results. In summary, this is a fast and robust method for orthopedic datasets where the radiodensity of bones is much higher than that of other tissues, but it is not as effective for kidney scans because of the overlapping radiodensities seen in those tissues. Further work on the orthopedic side would be to improve the morphological operations, and on the kidney side, another method would have to be used. Segmentation is another method that was explored in order to segment the bones and the tissues. Threshold mask is taken as input, and then an algorithm that uses seed points to select objects of the same radiodensity and separate them. This worked again for the knuckles, but it is prone to bleeding, where the seeds overgrow and connect to undesired segments, and also the meshes produced have no relative position information, and this would require a skeleton to make them a meaningful 3D object. In summary, this was not developed enough to implement in the final scripts, but it is worth pursuing further. The further work would be to fix those issues pertaining to the skeleton and the positioning and the bleeding. Marching cubes algorithm was used to create the meshes, identifying first an isosurface within the 3D voxel arrays of intensities, and then with this within logical cubes of 8 pixels and a lookup table shown on the right, complementary cubes are matched and the inner surface is determined. We look into the scikit image and the VTK implementations, and these are both evaluated in the testing section. In summary, the marching cube algorithm was implemented in order to create the final meshes. More advanced versions of this algorithm do exist, and they could be explored in the further work. Active contours. This algorithm was explored in order to conserve the labels as a product of segmentation from one frame to another. As seen on the right, this was used in 2D to follow the mouth of a speaking actor in the original paper. However, because we didn't fully automate the segmentation, it was not pursued, and the further work for this would be to explore that with a segmentation algorithm. The output, the files produced by the preprocessor are taken as input for the HoloLens viewer, and therefore the requirements for the output are dictated by the developers of the HoloLens. They required a 3D model of JPEGs. In each 2D plane, JPEG was chosen due to its high compression rate. Interfacing the preprocessor with the web application. First, the input files are in local storage. A child process is spawned in Node.js to run the preprocessing Python script. Files are created in a temporary folder during this preprocessing, and a JSON log is kept so that the created files can be uploaded to the blob storage and the database. The preprocessor was tested for both accuracy and runtime. Quantitative accuracy testing was undertaken by digitally creating DICOM images of a sphere geometry and then testing the properties of the produced mesh from those images against those of a sphere. Qualitative assessments were also made of these meshes produced by different implementations of the marching cubes algorithm, and assessed the details relative to each other. Pre-processing section of this project started with exploratory solutions submitted in the form of IPython notebooks. These notebooks aim to provide a guide to the implementation of the Python modules which implement to solve the manipulation challenges discussed. Implemented in the final script and embedded in the web app is a pipeline of validation, organization, manipulation based on threshold mask and marching cubes algorithms, and input with machine and human readable logs is produced to local storage. The web viewer serves to display visualizations generated by the preprocessor in the browser for users without access to a HoloLens, and it's integrated and hosted by the web app. Condensed requirements for the web viewer. The HoloLens uses only dynamic content provided by the preprocessor optimized for mixed reality. Intuitive user interface interacting with the visualizations is simple, and it resembles the UI of the HoloLens application. The web app requirements. It must fit in with the web app developed by Gun Winam in React and Node.js. The language chosen was JavaScript, and the library Three.js, which is a common animation library for JavaScript. The display style is slightly different from that of the HoloLens. It's 3D orthogonal multiplanar reconstruction. This shows the DICOM images above the produced mesh and takes advantage of all the files generated during the pre-processing section of the pipeline. A few implementation milestones: creating a scene, camera, and lighting to render the mesh objects within a bounding box, displaying the images in their corresponding orthogonal planes relative to the depth of the mesh, and then changing frames to give it a fluid four-dimensional view. Integrating with the web app was mostly undertaken by Gunwu Nam. It's a React web app, and the files are stored in S3 storage. For testing the web viewer, the interface and load times were tested, as well as the responsiveness and the interoperability across operating systems, as shown on the right. The web viewer serves as a simple approximation to the user experience of mixed reality application that is the focus of this project, a simple and robust application implemented using JavaScript library Three.js. There is a known bug where it comes to scaling the object mesh in the Z direction. This may be fixed with an update to the preprocessor output bounding features. So the demonstration is a prototype application produced using Node.js and Express as a back end instead of the web application. It takes the raw input of 4D image files and produces the meshes in order to show them on the web viewer. Just going to speed it up slightly, although it all comes out within the functional requirements for time. First, the 4D dataset is uploaded on the prototype application as shown on the right, and the server log is shown on the left. It goes through the process of validating and organizing the slices, and the human readable logs are shown there. We can see that we have 39 frames and a total of 5,633 slices. A data cube is created, which is a 3D voxel array of the images, and then for each frame a mesh is produced of the 39 frames. As soon as that is done, we will be able to see the frames in the web viewer on the right. So now they're all done, reloading the viewer page on the right shows the mesh loading very quickly. We've got orbital controls so that we can see it from all angles, and we've got 3 sets of controls. We've got a slider to change the frame, we've got a slider to change the opacity of the mesh, and we have sliders showing the JPEGs that pertain to the DICOM slices in the 3 planes. These are positioned to overlap on the mesh, as you can see. Thank you very much for listening. If you have any questions or feedback, there's my contact details.